Hi, my name is Radha Panchap. I'm joined by Gabriel Granados and Christina Chance, and our project is housing market price prediction. The problem is that there are high arbitrage opportunities within the housing market, leading to realtors overcharging more than the listed price and buyers often overpaying for a house. We'd like to better understand which features most contribute to the price of the house, and our machine learning project will allow buyers to understand if they're being charged a fair price given the characteristics of their home. So in regards to the data set, there are 18 columns and 4601 entries, and there are some key features such as square feet of property, number of bedrooms and bathrooms, and whether it's a waterfront property. The data is from 2014, and there are some features that need to be pre-processed.
Our pre-processing was to remove data that were outliers and would negatively impact the performance of the model. Based on other iterations of projects and use of this data set, a large issue that others faced was some records having the price equal to zero. Logically, that is impossible, and other features possess similar trends of values being set to zero when there wasn't a valid variable. Additionally, we transformed the values like zip codes into categorical values so that the value of the zip code wouldn't be used as a quantitative correlation. We also scaled the data so the extremely high and ranging values wouldn't influence the coefficients. Here are the correlation matrices used. On the left it is representing how the variables are correlated to one another and related. And on the right, it shows the relationship between the features and the labels, which are price. For findings, after using the correlation matrix and other pre-processing tools, we created a list of features we would use to reduce dimensionality. But in the preliminary stages of our project, we saw that the model performed significantly worse using metrics like R-squared and mean squared error in order to calculate the accuracy. So we decided that we would no longer drop these features. For modeling and methodology. For our methodology, we use supervised and unsupervised learning to better understand the data set. We use PCA as a way to hopefully reduce dimensionality further. As for the models, we use a variety of models to better learn the relationship between the data and our labels. We use the standard ones like linear regression, lasso, and ridge, as well as random forest and decision tree regression.
These are the PCA results. We can see the explained variance ratio. For the first one, we see that the first PCA explains 33.6% of the ratio. I've also highlighted the features that corresponded to the highest variance explained per PCA. So we can see that the 8th feature had the highest variance for PCA 1. And so these were the models and coefficients of the features. And so just wanted to show this here. And in regards for evaluation, we use k-fold cross-validation, and we used error metrics such as MSE, MAE, and RMSE in order to understand how the models performed, and also R-squared. And so the summary of the k-fold results was that the random forest, ridge regression, and linear regression had similar performance. Ridge and linear regression had a train R-square of 0.65, and their test R-square was around 0.55. And furthermore, the SGD performed considerably poorly, and the decision and tree and lasso regression were overfitting. And so because of this, we decided to do some hyperparameter tuning. And in our methodology for that was creating lists for each hyperparameter within each model and using grid search to find the best parameters. And so I'll hand it off to Gabriel to explain our results.
Yeah, so like Rada said, we use grid search CV to find these the best parameters for each model. So what we did was that for each model and for each parameter, we would graph the accuracy just based on a range of different parameter values. And we use that to kind of find the optimal one. So here we can see just the different parameters for each model and how they perform in terms of the training accuracy. So after looking at the hyperparameters and how our models perform when we plug them in, we were able to get models that don't overfit. So for example, our optimal lasso regression had an R2 of roughly 0.63 and random forest 0.76 and decision tree 0.38. Out of all the models, the best ones were ridge and lasso, which seemed to perform very similarly. The optimal decision tree and the stochastic gradient descent seem to be the worst performing. And we believe that's because the data set works with large numbers, and therefore SGD may be worse performing because of the step size. It could cause it to not reach that optimal solution. Neither model is terribly performing though. Historically, random forests are supposed to be better since they use the bagging approach. Overall, our models perform similarly to models seen on the Kaggle competitions though.
Yeah, and so these were just the k-fold results and the SGD results. Thank